Hello, this is the helper video for AC to DC rectification regulation. So this is highly important in terms of any devices that you use at the moment. So in terms of your chargers for your phones and laptops, things like that. So your 3-pin socket where you plug into your devices will be 230 volts AC, and that is at a frequency of 50 Hertz in this country. So that needs to then go into a charging device and then hook into a laptop or a phone, something like that. So this could be a laptop or a phone. Now, a laptop and phone is working on a direct current, so that is DC. And usually, you know, for a laptop, it could be 12 volts. A phone, it could be less than that, it could be 5 volts or something like that. So this, as I say, is really important. And this block here, which is your charger, is the block we are, or the circuitry we are focusing on. Okay, this is where the rectification and regulation are, there's a function that happens in here to translate AC to DC. So we did talk about on an earlier session about AC and DC. So AC will generally have the waveform of a sine wave, continuous sine wave, so that is AC, and DC is a flat level, so that will be, you know, your 12 volts in here. This, as we said a minute ago, is 230 volts, and that is from the power sockets. It's 230 volts, but it's an RMS value, 230 volts RMS. So this was covered on a previous video helper. So in terms of the peak here, this will not be 230 volts, this will be to another value. And we can actually calculate that. So that V peak value there is the VRMS, and it is multiplied by √2. Let's say that the actual derivation of that is covered on another helper video or in the notes. So we did that calculation there. Then we'd come up with 230 volts multiplied by √2, and that should come up with around 273 volts RMS. Oh, sorry, peak. That's V peak. Okay, so that is, and obviously the value that goes down here will be at, on the minimum, is minus 273 volts. Oops, correct that. Give me a bit more room. So that is minus 273 volts, and this is plus 273. Same again, okay. 273 volts. Right, okay, so so we need to basically get from that to a nice flat waveform for DC. So how do we do that? Well, one of the devices that is really useful in being able to only allow the positive through and not the negative, i.e. allow current flow in one direction but block it in the other, is a diode. So we're going to use the diode component to first of all get rid of this negative bit here, because this is the negative part and this is the positive. That's sort of the first stage. So that process is actually called a half-wave rectifier. So the best way to show this is in a simulator called Falstad. So here we go. We have, this shows the electron flow from an AC waveform of 50 Hertz, and it goes from positive to negative and flicks around negative to positive. Okay, so that's the way it works for AC. On DC, that would flow in just one direction. So we're only really, after half wave rectifier, we're only interested in the positive. So the way we do that is we connect in one diode, and as you can see, the electrons flow and then they're blocked. They're blocked on the negative. Okay, and then but they're allowed through on the positive. So let's just screenshot that. Quite useful to have this. Put it into our helper notes. Okay, and that's what we got. That's one diode, and that's, you can see the output waveform is on this right hand side here. So we can put that in as well. That obviously is not what we want for our DC. We need something flat and positive. So the next progression is to go to what's called a full wave bridge rectifier, because that has, and why it's called a bridge is particularly because the way it looks, where it has four diodes in here, and the reason why we need 4 diodes is that we need to cycle through, so it allows non-ground connection if you connect a transformer in there, and I will come on to that. But this is a full bridge, so you can see that on the positive cycles it flows through a pair of resistors, a pair of diodes, and on the negative it flows through a different pair. Okay, so if we screenshot that, you can put that into there. And that gives you a feel for how it works, because this is the output waveform now, and as you can see, that is a positive sort of hump waveform. We move the negatives into the positives. I can screenshot that in as well. I can kind of show both the input and the output as we put underneath. Okay, right, so that obviously is getting there, isn't it? But it's not quite there because it's not smooth. So how do we achieve the level smoothing? Well, the way we do it is we use a component called a capacitor, which we've talked about before, which charges and discharges. So it is capable of smoothing the waveform. So we move on to the next circuit, and we can see that there is a capacitor in that circuit. And as you can see, it is charging and discharging as it goes along to smooth out the humps that we had earlier on. Okay, so it's pretty much getting there in terms of a much flatter waveform. So again, we can put that, we can screenshot that in, and we can include the input and the output in there and put it into our next progression. Okay, so the next thing is it's not so that this is with, so, and we can actually have a little play with this actually in the simulator, so we can see let's change the capacitor value. Let's change it to a smaller value. So if we go back from it's micro, go to nanofarad, a small resistor. Let's see the effect on the waveform. So you can see it's much bumpier. The charging and discharging is not happening on a slower rate because capacitors deal with the changing voltage over time. So if you put a larger capacitor in there, it's going to smooth to a much nicer, smoother, slow changing, charging and discharging. So if I made this much bigger and we applied it, let's look at the waveform we get. And that's actually much, much smoother than the micro. We go back to the micro, we can put that in there and show the effect of that. Okay, so that circuit there is rectification. And if we go back to what we had here, so this is a full bridge rectifier with a capacitor smoothing on here. Smoothing. Okay, and we're not quite there yet with the flatness or the flat DC. So the way we end up achieving the flat DC is we end up adding yet another component in there, which is a Zener diode. The Zener diode is able to clamp that waveform there. So this waveform here, so what I would do is I would add in, let's see if this shows up in here. Oops. Yep, so we'd add in a Zener diode in here, which would then, and this is reverse bias. So a Zener diode in reverse bias which effectively clamps the waveform underneath that ripple in the voltage. So you'd end up clamping it underneath. If that was let's say a 3 volts Zener diode in there, that would clamp it at the 3 volts underneath this ripple. So let's say this is ripple voltage. So the function that the Zener diode does is it clamps under the ripple. So this is also given the technical term as regulation. Effectively regulates the voltage so it's nice and smooth underneath that ripple. Okay, so we then, that is the last stage of rectification and regulation, and you should get a pretty much smooth, straight DC waveform at the desired 12 volts or 5 volts. You choose your Zener diode for that clamping underneath it, which how the Zener diode works is that it actually acts like a barrier, and when the voltage is in reverse bias mode, it allows the breakdown underneath the barrier at that voltage. So we will summarize diodes and Zener diodes later on in the course, but that just gives you the idea on the progression from AC to DC and shows you what components are involved in doing it. The best way to visualize this as well is to think of you traveling through the circuit as an electron. Which path would you take? So if you're going up this part here, I'll try a different color. These don't work. Let's just do red again. So if you're an electron and you're going this way, which path are you going to take? Well, the diode is in forward bias, so it would choose to take that one. It would be blocked from this one because that would be reverse bias, and then it would go traveling on through the load resistor back through here. Which way do we go? This way? Well, we go the forward bias, and then we can't go, we're blocked off this reverse bias, these two here, so we end up going right round there back to the terminal. And if the electron goes the other way, it's the same principle. So if we went to, if an electron going this way, we would go up through here. We come to this point here and we decide we're going to go forward bias, and then we're going to go, I just need to move this across. We need to go across, round the load. In this case, we get it smooths as well. Up here, we decide we're going to go forward bias, and we're going to go back to the terminal. Okay, that's the way it works. Okay, so that's, just think the electron traveling around the circuit. So I think that really concludes this helper video, and we've covered all the way from AC to DC, just like your charger for your laptop and your phone. Okay, and I will see you on the next session. Thank you.